looking at search engine optimization. I'm going to take a break from that now, and we will return to that. But I want to start looking at some of the ways images are coded and the ways that we can optimize them so that they take up less space when we put them online. You might recall when we were doing web development fundamentals, someone might have told you that, you know, if you have an image that's 4,000 pixels by 4,000 pixels and it's only going to be displayed 400 pixels by 400 pixels on the page, that's very wasteful because it would be 100 times bigger than it needs to be. So that's costing somebody money somewhere. And if it's not, it's, you know, destroying the planet. So we're going to look first at black and white images because it's that little bit easier to conceptualize. When we go to digitize an image, thinking about black and white ones is a bit simpler. So when we have an image that we want to digitize, we break it up into non-overlapping rectangles. Now those rectangles are often squares, but they needn't be. They don't have to be squares. And what was I going to say? Yeah, digitization is simply the process of representing some things numerically. We often use the word digital as though it's synonymous with quality, but it's not necessarily. So we think about digital music and we think, oh, that's, you know, high quality, but you can have low quality digital music. You can have low quality digital images. So digital doesn't mean high quality, it just means that it's stored numerically. Now once something is represented numerically, you can make perfect copies of it because you're just copying the numbers. But that's separate from the quality per se. So we break the image up into non-overlapping rectangles and then we look at each one close up. So if we consider this one here, we would get the average darkness of that particular space, and then it would fit somewhere along this scale here. So that particular shade, so let's take this, you know, this shade of light gray here, that would land somewhere perhaps here. So on this continuum from black to white, which is infinitely fine, there would be ranges there, and you would slot that shade of grey, would fit into one of those ranges. So let's say I wanted to record everyone's height in this class, but I didn't need a whole lot of precision. I might line you up against the wall and count how many bricks you have. So like you'd fit into, you know, 1, 2, 3, 4, 5, 6, 7, 8. You might fit in between, you know, the 7th and 8th brick. Someone might fit in between the, you know, 6th and 7th brick. And we call each of those levels, we call those quantization levels. So in this image here, we're just looking at having 16 of those. So here, the average grayness of one of those rectangles, there may be, you know, infinite precision, infinite subtlety in there, but we're going to slap it into one of these 16 ranges. So the digital image then is made up of small rectangles called pixels. Sometimes in the literature or in books you'll hear them called pels, picture elements, pels, but pixels is much more common now. And so each pixel's color is the same as the average color of the part of the image that it represents. Now, the quality then of the digital representation can depend on a number of things. So obviously the more pixels you have, the better the quality. So we often hear people talk about dots per inch. Even in the metric world, you still hear people use dots per inch. And so on a screen, they might talk about dots per inch, and when you're scanning a document, you might decide how many dots per inch it's going to be. And if you consider an inch of a photograph, let's imagine we're putting a photograph into a flatbed scanner. If you consider an inch of that, well, if you have like 800 dots by 800 dots for every inch, that's, you know, reasonably high resolution. If you had 100 dots by 100 dots, that's not going to look as good. Now, depending on what you do with the image, it might be fine. I mean, if it's going to be put on a web page, you know, the screen isn't many dots per inch anyway. If you're going to enlarge it the size of this wall and make a huge poster out of it, well, it's gonna not look great. You're going to start seeing the pixels. So the more pixels you have per unit of space, the more precise the digital representation of the image is going to be. And that's something that applies with all kinds of digitization. Same principle. So here I have the image at 600 pixels by 400 pixels. And if we reduce the number of pixels used here, now it's only 300 pixels by 200 pixels, so we've thrown away every second row of pixels and every second column of pixels. So there's only a quarter now of the information in this one. And I think you can already start to see there on both my screen and yours that it's not as good. You're starting to see the pixels. And this one I can't see the pixels, you know. I don't think you can either. But certainly at 300 by 200 you're starting to see them. If we go to 150 by 100, then you can clearly see the pixelization. And if we really push the boat out, you know, it's starting to get ridiculous there at 75 pixels times 15. Now we could actually count them. You know, we could go like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. See the actual pixels there. So the more pixels you have in an area of space, the better the quality. Now I think it doesn't make sense to consider the number of pixels all by itself. You know, I mean 75 pixels by 50 pixels on a picture on my thumb would be fine. 600 pixels by 400 pixels if I went to a chemist and printed those out on paper, you'd actually start to see the pixels. If we printed this out, you'd see them. It's just we don't realize it, but the screens we have are actually really not very high resolution. And we're looking at them far away. So the more pixels you have, the more accurate the representation, but it depends what you're going to do with it. Now, if we go back and consider here the number of quantization levels that we have. If I lined you up against the wall, I didn't shoot you, but just counted how many blocks high you were, you might find that it's not a very fine representation of the differences between your heights. You know, most of you might be on between the same borders of the blocks, and it might not be a very precise measurement. If we had smaller blocks, then the differences between your heights might start to become apparent. But of course, if you have smaller blocks, you've got more quantization levels. And the more quantization levels you have, the more accurate the representation is going to be. But of course, also, the more bits you need to represent each one. So if you've got 16 quantization levels, you only need 4 bits. If you've got 256 quantization levels, you need 8 bits. Typically, for a black and white image, 8 bits per pixel is plenty. So when we scan an image and store it in black and white, typically we use 8 bits and 1 byte then per pixel. Here is the image at 8 bits per pixel. And it turns out there isn't really in this image, I think, the full range from black to white. Like, I don't think there's any pure white in this. And I think even this black part here, I don't think that's even pure black, you know. So in this image, we're not even using the full 256 colors, I don't think. If we go down to 5 bits per pixel, I don't think you can see any difference at all. And so with 5 bits per pixel, we've got how many shades of gray in there? 2 to the power of 5 is 32, isn't it? Or is it 64? It's 32, isn't it? So there's only 32 different colored pixels in here. And actually, I think it looks fine. So, I mean, if you were on holidays and you were posting this image to your Facebook page and you were paying roaming fees, this might cost you 80 cents, where this would cost you 50 cents. I think the 80 cent one represents very bad value, really, because you can't see the difference for the 50 cent. Next up here, we've only got 4 bits per pixel. You can just about make out a difference there. Up in this area here is where it's starting to give way. So where you have a smooth gradient, that's where you'll start to see it first. And just up there, the top half of that middle column, when we go to 4 bits per pixel, it starts to go a bit. So here we've only got 16 different shades of grey in this image, and it's actually holding up quite fine. At 3 bits per pixel, we've only got 8 shades of grey, and it's starting to get a bit ropey now here. So you can see that the smooth gradient in here is gone. So it goes from this colour immediately to this colour, and immediately then to this colour. So there isn't that smooth transition. So generally what happens when you reduce the number of quantization levels, a value will fit in, a value that fits in a range will just be represented then by the middle of that range. So the smooth gradient will start to give way, and we'll see more of that later. Now there are things you can do to help with that. When we go down to 3 bits per pixel, you see you can start it starting to give way there. If we go to 2 bits per pixel now, we're really pushing the boat out now. So 2 bits per pixel, we've got 4 shades of grey. And you can even count them. I mean, there's this dark one, light one, next one up, and then this kind of white here. So there's only 4 kinds of pixel in this image. But each pixel is only using up 2 bits. So this would cost 20 cents to send as opposed to 80 cents. But I think it's, I think you can be too cheap as well. Maybe the 3 bits per pixel here, that would be 30 cents. Maybe that represents good value. Or, I think the 4 bits per pixel is a good compromise. 40 cents there would cost. You could go all the way down to 1 bit per pixel and pay 10 cents. But that's kind of pointless. So this is just pushing the boat out too far. And here there's only 2 kinds of pixel. Dark ones and light ones. So this might be 0. This might be 1. Now, as it turns out, there are some kinds of images where that's perfectly fine. I mean, a fax, could be 1 bit per pixel. Okay. Any questions on that? So there are two things that are affecting the quality and the size of the image. The first thing is the number of pixels, the resolution, the number of samples you have per space. And then there's also the quality of each pixel, the quality of each sample, and how many bits you use to represent it. And when it comes to digitization, we come across those variables again and again. So like when you digitize sound, you talk about how many samples per second and how many bits per sample. So if you're converting music in iTunes or some program where you're saving it, you have the option of reducing the sample rate and also reducing the number of bits per sample. Similarly with video, there are things you can do there. Now, so that's black and white. And when it comes to converting something in the real world, an image in the real world, to digital form, we are concerned with black and white. It's fairly easy. We look at the value we want to represent, and then we fit it into one of the quantization levels. To understand, to digitize something, to represent something with numbers, you have to put order on it. And I think if I was to give you 1, 2, 3, 4, 5, 6, 7, 8. If I gave you 8 shirts there lined up on a rack and they were all shades of grey, and I said to you, right, I'm really, a bit OCD, I want you to line up these shirts so that they're in order. It would be very easy to do. You put the white one at one end, the black one at the other end, and just line them up in order, they're shades of grey. Now, if I brought you to my house and said, okay, I want you to organize all my shirts in order. How do you do that then with color? That's not so easy. I mean, we know blue and green are different, but, is green more of something than blue? I mean, it's more green. Green is greener than blue, but I mean, how do you put order on color? I mean, if these are 6 shirts in my wardrobe and I ask you to put them in order for me, line them up in order, what comes first? When they're all grey, it's pretty easy. You could put black at one end, and work your way towards white, or you could put white and work your ways towards black. But with color, it's more complex. And it turns out color is a whole lot more complex. So what we're going to look at in this class and the next is some of the ways we put numbers on color, some of the ways we order color. Watch the time there, guys. My clock doesn't work anymore. So the first system we have is the hue, saturation, and brightness model. I find it a bit hard to get my head around the notion that the light that we can see with our eyes is actually the same kind of stuff as radio waves. The stuff coming out of the transmission tower in 96 FM is the same thing that's coming off my laptop case and coming into my eyes. It's just a question of the frequency, but it's the same stuff. It's all part of the electromagnetic spectrum. And as humans, we are sensitive to a certain portion of the electromagnetic spectrum. We can sense it with our eyes. Once we get into ultraviolet and infrared, we can't see it anymore with our eyes, although we can sometimes see it interacting with other things, or we can feel it. Different species of life on the planet may see different parts more or less. They may see a different range. And if you came from a different planet, you might see things completely differently. So humans can see a portion of the electromagnetic spectrum. And the rainbow features quite significantly really in the hue, saturation and brightness model. So we can see roughly from somewhere like kind of 720, I think, to kind of 400 nanometers wavelength of light. And that's something we could use to put order, to put numbers on color. We could say, well, look at its wavelength. So we could organize colors by their wavelength. So you could imagine if I gave you color chips, you know, or if I had a shirt from each of these ranges, you could say, well, I want you to organize my shirts now. And you could look at the wavelength of them and go, oh yeah, okay, there's something I can see there. And this is essentially like kind of a rainbow scale, where you've red at one end, you know, green in the middle, blue at the other end. The problem though, well, we call this the hue, okay? So the part where a color fits on the rainbow scale would be the hue of the color. And that's the relationship between that and the frequency of the light. The problem though is that there's more going on than just the hue. I mean, there's no pink in the rainbow. There's no white. There's no brown. There's no black. There's no grey. So there's more going on than just the hue. But the hue is certainly one of the things we can work with. So if we look here, all these different shades of kind of bluey green, they all have the same hue. But they're quite different colors. Similarly, these shades of yellow here all have the same hue. We can all accept that each one of these colors is in sort of the bluish range. I mean, if you said, you know, on this scale here, from red to green to blue to purple, this is clearly bluish, and this is clearly yellowish, and indeed this is clearly, you know, purple-ish. But there's more going on. And it turns out that color can be diluted. So you imagine if you have a cup of hot chocolate, it's nice and brown, and you add some milk to it, it gets a bit paler. You add some more milk to it, it gets a bit paler. You can dilute color. And saturation is a measure of the purity of the color. So like highly saturated color is pure, and then a low saturation will give you maybe a shade of, you know, tending towards grey. So pink, for example, is like a red with the saturation turned down a notch. So if we look here on the left, we have highly saturated color, and on the right then we have low saturation. So I mean, we can accept that, you know, oops, my cursor's gone, that the one on the left there is green, and one of the ones right in the middle is also green. And their hue is the same. I mean, they're the same, you know, it's not like one is tending towards bluey green or one is tending towards a, you know, yellowy green or something. They are green, but one is just purer than the others. So when the saturation is high, you get a pure color. Actually, on your screen, they look a bit yellowy. No. So saturation is to do with the purity of the color. And if it's strong, you got high saturation. If it's faded, you know, it's low saturation. But it turns out that hue and saturation even by themselves aren't enough. So here, for example, every one of these colors has the same hue and the same saturation. But there's more going on. And what's going on is the brightness. And we're kind of on familiar territory here, because brightness is just the amount of lightness or darkness in the colour. So if you imagine you're in a shop and you can buy light bulbs. You know, some people love coloured light bulbs. So you want a coloured light bulb for your man cave or your home bar. Okay. So you go into the shop and they come in red and blue, and there's like a whole range of possible colours there, a whole range of hues. But then looking at the bulbs, like say you want to go for red, looking at them, some of them are very, very pure red. The glass in them is really pure. Others then are a bit paler, so you can sort of get maybe almost a pink looking one. You come home and you plug it in, okay, and you can turn it on and off and it works fine. You have a dimmer switch. If you turn the dimmer switch up fully, the brightness is up fully, it's still red, it's still quite high saturated red, and it's fully bright, but as you start to turn down the dimmer switch, eventually you'll end up with black because the light will be off and there'll be no light. So you've hue, saturation and brightness, three different things that interact. So if you were to organize all my shirts, it wouldn't just be one row, one hanger, right? You'd actually need to work in a three-dimensional space. You'd need a huge closet. So you'd have to go from left to right, up and down, and even go back. So you might have hue from left to right, saturation up and down, and lightness and darkness going back. So you'd have red here, orange, yellow, green, blue, indigo, violet here, low saturation down the bottom, high saturation up high, and then at the front you might have the light ones, and way at the back you might have the dark ones. You might find way at the back you just have a wall of black shirts. So you actually need three variables to represent colour. So you need to think of it as a three-dimensional grid, whereas for black and white it's just a line, black here, white there, all the stuff in between. So hue, saturation and brightness comes quite naturally to us as humans because we're familiar with kind of the rainbow scale. We've seen rainbows, where the concept of like strong colour and weak colour, saturation, is fairly familiar to us as well. And lightness and darkness, we get that too. So hue, saturation and brightness is the best one when you're dealing with humans, but computers work better other ways. Now, hue is usually expressed as a circle with a number of degrees. Saturation is usually expressed as a percentage from 100 to 0, and brightness is usually expressed as a percentage from 100 to 0. A really good way to get to grips with how color systems work is to go into something like PowerPoint and decide to change a color, and you can call up the color wheel that's native to the operating system. And so here, for example, we have, I'll just turn up, so here we have, as you go around the wheel, the hue changes, and you'd measure that in degrees. So here we have an orange between red and yellow. As you can move in, I'm still on orange now, but I'm reducing the saturation. It's starting to get paler. So you see how it goes from being orange to being sort of a, what would you call that? Creamy colour, whatever. And then you can also reduce the brightness. So here I'm reducing the brightness now. So it's still creamy, it's just getting like, you know, dark. And if you turn the brightness all the way down, you'll eventually get some sort of black. You can also, depending on the system, use sliders. So here, if we, I'll turn up the saturation again. So we can see, you see that the hue starts at red at 0, goes through orange, it's like 42 degrees, through green there. It is interesting that green takes up quite a lot of space and blue takes up quite a lot of the range. Yet we've, for various reasons, we've decided to break up this tiny range here into indigo and violet and give that two names. So you see it goes up to 360. You can reduce the saturation. As we reduce the saturation, it gets paler. So you see when you turn red, when you get red and you reduce the saturation, you end up with pink. And if we turn down the brightness, go down there. So you'll find this in you know, Windows machine as well. Like you go into PowerPoint and just try to give something a color, and you can see that happening. And that's a really great way to get to grips with how it works. Now, RGB is the system that we see most of in computing. So computing systems use RGB, red, green, and blue. So we have one value that represents the amount of redness in the color, another value that represents the amount of greenness in the color, and another one that represents the amount of blueness in the color. Now you might remember from physics class where you have a red light and a green light and a blue light shining onto a white surface. Where they intersect, you get the appearance of white light. Where the red and the green intersect, you get yellow, which is kind of counterintuitive. But you're not mixing paint, you're mixing light. And when you mix green and blue together, you get cyan. Okay, this is interesting now because your screen is completely screwed up. Okay, so what I'm trying to show you is this thing here that you have seen in physics class. And if you look at your projector there, which channel, which thing isn't working? The red just isn't working. So there's no red whatsoever in that projector. So the bit that produced the red is just completely blown. Okay? So that's interesting. Now, so some of these will look very strange. So here, this is pure red, but you can't see it all. Okay? So you can see on my screen there. So when the red is turned up fully, now the red, green, and blue values, they range from 0 to 255. Why do you think that is? Because you can get, in 8 bits, you can represent from 0 to 255. So 1, 1, 1, 1, 1, 1, 1, 1 is 255. 8 bits, 1 byte. So when the red is cranked up fully, and the green is 0 and the blue is 0, you get pure red. Here, the red is 0, the green is 0, and the blue is almost full, almost up to 255. It's quite high. And now the higher the values, the brighter it's going to be. So here the blue is 200, and blue is the only color at work there, so that's going to be blue. When you have red and green together, you get yellow. So that's interesting because I would have thought that would have come out wrong. But I guess in the big screen it's a bit green, all right. But I would have expected that to not work nearly as well as it has, because it's quite yellow even on your screen. So where the red is turned up fully and the green is turned up fully, you'd see yellow. Here, we just have the, look at my screen here now. So we have the red is 0, the green is 178, and the blue is 0. So green is the only thing at work here. So this is going to be a shade of green. The only question then is, what kind of shade of green? Now 178 is about halfway. So it's, you know, it's not going to be super bright green. It's that shade of green there. Here, again, only green is at work. There's no red, no blue, so it's only green, but it's darker because the value is lower. Where the red and the green and the blue are equal, you get a shade of grey. Here, 200 is quite a high value, so it's quite bright. But when we go to 150, so red 150, green 150, blue 150, you know it's a shade of grey, but 150 is a bit darker. 80, 80, 80, again a shade of grey, again a bit darker. When the red and the green and the blue are all cranked up fully, you're going to get white. What do you think's coming next? When the red is 0, green is 0, and blue is 0, you get black. No. In HTML, colors are expressed in hexadecimal. So that's, you may recall having seen, you know, hash 8080 FF, that kind of thing. All that's doing is representing the colors in hexadecimal. I wasn't going to do this exercise yet. Okay. Here, you won't. Hang on, I have to turn my screen around again. Sorry. So the red value, the green value, and the blue value for each pixel is stored. And often it's useful to look at just the red, just the green, and just the blue. And we call those different representations channels. So here in the red channel, the difference between things that are white and things that are red is hard to appreciate, because something that's fully red would have a high red value, and something that's fully white would have a high red value. So they both would have roughly the same value. So in the red channel, it's hard to see the difference between red things and white things. But in, say, the so here in the red channel, for example, here it's just represented as black and white for high and low. The difference between the red stripes and the white stripes are hard to see, whereas in the green channel, they're quite obvious, and in the blue channel, they're also quite obvious. Here, I had 3 doors. You can imagine my delight when I saw 3 doors lined up for myself there, red, green, and blue. And it's no great surprise then that in the red channel, the red door appears the brightest. In the green channel, the green door appears to be the brightest. And sure enough, in the blue channel, the blue door is the lighter of them. It has the highest blue values. I'm going to skip past that. An exercise we could do, except your screen isn't working, so you won't even see the same colors I'm seeing. Blah, 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 blah. What time is it there? Okay, we'll leave it so. And then the next day, we'll look at the LAB system. Also, I put a link to a movie online I want you to take a look at. Great stuff, guys. Thank you.